Okay, hi everybody, welcome back. This is the solution to your second challenge. So if you recall, we wanted you to do something like this. And then write it to a file and capture what you did. All right, so let's dig into how we do that. So you're gonna see, I'm gonna borrow some code, as we always do. I'm gonna open up the dummy template, copy it, paste it. I'm gonna make a new tab, like we did last time. I'm gonna call it comb. I'm gonna make a new class called comb. You're done. Not exactly. And like we've done in the past, we're going to give it two standard public methods, the perform method, and a comb filter will take an input, and it's going to take a delay time, and we're going to give it a gain as well, which gives it a little bit of spice. And we also need a free method, as we always use. And we are going to just make it real simple. We're going to only have two things in this. We're going to use the variable delay class, which in pure data is called VD. Kind of a weird name. Oh yeah, new, forgot the new word. And we're also going to need a double called a delay. And this is going to be our output to our delay. That should be all we need. Yeah. So ultimately we're just going to return the delay. And what we're going to do inside the perform is we're going to use the variable delay, and we're going to write to it, and then we're going to read it back into itself. So the first thing you have to do is use the member function of variable delay, which is delay write. So in pure, if you're trying to compare this to pure data, if you're coming from that world, delay write is its own object. It just literally writes to a delay buffer. But I wanted to just keep life a little bit easier, so I just put it inside of variable delay. And it's just, that's just the way it is. So we're gonna write our delay to itself. This is our feedback stage. And that's all you have to do. It doesn't return anything. It just writes to the delay buffer. And then we're going to read it back in using the perform method of variable delay. And that will be where we give it our delay time. And this is what fits the convention of PD. When you give the input to variable delay, it's delay time, which could also be a signal. So that could be, you could use an oscillator or something like that if you wanted some really wild effects. And we're just going to add the input to itself. So now the input and the delayed input, delayed output are added together and fed back into itself. So this is a feedback system. And we have used all of our arguments. So this is looking good. So now we're going to go back to our dummy sketch. And we're going to need, actually, let's see. For now, we're going to just need a few variables and a few objects. So we're going to make a new comb object. Okay, so we already did that. And since we made this class ourselves, we didn't make it static. So we're just going to do comb free. And did we free it here? No. Variable delay dot free. The only reason why we have to do variable delay dot free and then pass the variable the object to itself is because these are static within the Java library, and that's the way you have to do it. But we don't have to do it that way. We could do it that way too if you wanted to keep the convention, but let's just not do that. Instead, let's just call it here with the name of the variable .free, like you would any other method. And then we're just gonna comb noise. So we're just gonna filter noise with our comb filter, and this is gonna be our delay time. We'll actually set it to 10, and we're gonna here call this set delay time, and get delay time. Delay time, turn delay time. And here it's just going to be comb perform noise dot perform. So that's our input, is the noise. The next one was our delay time, so get delay, spelled incorrect, delay time, which maybe we haven't done this explicitly before, but you can put, if anything returns the proper value, a float, well, it's actually a float. Yeah, it's a float and a double. In Java, they don't seem to care. Floats and doubles are both floating point with different levels of precision, so the casting is done for you. So you don't have to worry about the difference right now. There is a difference, but we don't have to worry about it. And then we're just going to give it a time right now, which is 0.9. This, I'm sorry, a gain. The gain is going to just be 0.9. That just basically means 90% of the original gain is going to be fed back. So we can hear it. And then I'm actually going to just scale this down a little bit because it's going to be kind of loud, because we're dealing with full volume white noise, so let's not blow our ears out. So the only thing we're changing right now is the delay time, and we're going to do that up here as we have before. We're just going to call it dt to keep the variables distinctly different between the two worlds of the processing layer and the audio layer, and we'll give it the similar value to start. And then we do what we've done before, which is we're going to map it to the x of the window. So that's the width. And then we'll go from, since this is delay time, about, let's say 0.5 to 50 milliseconds. Yeah, so that's one thing I didn't mention. Delay time is in milliseconds. You would have potentially found this documented somewhere in the code, but it's good to know. We're just going to call this condemo. All right, now we got 2. Okay, so this should now delay our input multiplied by our gain, so it's not going to be out of control. The delay time will be mapped to our XY, and then we're going to set it in our music layer. So that's music.set delay time dt. All right, let's see if this works. Cross your fingers. Excellent. So that's a really spicy comb filter right there. All right, let's also be able to adjust the input gain. So we're going to call it delay gain, and we're just going to give it a value of 1. And now we're going to add a getter setter for that too. Synchronized void set delay gain, and we'll give it a float g. And easy enough, delay gain. Why am I not spelling that? Delay gain equals g. Done. Synchronized float get delay gain, and all we have to do is return delay gain. Boom. Now we can change this here to get delay gain And we can add a new variable up in processing land, delay gain. I'll just set it to 1. So remember, gain in audio world is between 0 and 1. And anytime you multiply that number between 0 and 1 to anything that's going to the output, it will change its volume. Okay, so it's good old-fashioned math. If 1 is our maximum output and we multiply that by 0.2, that brings our volume down to 0.2, or 20% of the output. So we're going to map that to the y-axis of our window. So 0 to height, and the gain needs to be between 0 and 1. But if it's really quiet, you won't hear anything. So we'll do like 0.4 to 1. It should be fun. Okay, so now everything except our input is controlled by our x and y. And expected token, because I spelled synchronized wrong. Synchronized, that doesn't work. And there it is, the classic forgot to set it. Set delay gain, DG. I was thinking that was way too low. Okay, and the constant reminder that y goes from top down. So we put our high number here and our low number here if we want to go from bottom up. And we don't need to test that. We know that's something that we do every time. Okay, so now let's go ahead, and I'm actually going to add one more step. I want to, the noise is a little too crunchy for me. So I'm going to add a bandpass filter. And I'm just going to bandpass the noise a little bit. And so we need to calculate our center frequency from our delay time. And if you look it up on the web, you get the fact that basically, since we're dealing with delay time in milliseconds, it's the delay time, or the frequency spacing of a comb filter, which is basically where the comb's placed. So what's the frequency spacing that the combs are placed? That is going to be 1 divided by the delay time. And the delay time is in milliseconds, so that's it's 1 divided by delay time converted to milliseconds. So it's just 1,000 divided by the delay time. So delay time is get delay time. And if you didn't catch that, don't worry about it. So we're actually going to be set the Q. I'm just going to set it to a little bit thinner bandwidth, to BP set center frequency. We've done this before in previous tutorials, and I'm actually going to set the center frequency to be about 8 octaves of that. So center frequency times 8. So we got the 1 octave. Basically, what is 1 octave, or 1 comb, is 1,000 divided by the delay time. And then I want to actually noise to be 8 combs wide, just so that it's not really crunchy sounding. And then we're going to, instead of trying to put all that nonsense inside of our argument, we're going to just do it here. So we're going to do bp.perform and put noise.perform inside of it. And that should get us now some bandpassed noise, then comb filtered. Let's try it. Okay, so there's some interesting sounds that you can make out of this, and you could add some more details and layers to it, and then you're like, wow, I would love to make a recording of this. How come there isn't just a button I push to record my sketches? And you're asking a lot from processing, but not a lot from Pd4P3. So all you have to do is go to the write sound file example, and you just look at what's happening here. And basically what you do is you're going to write everything into RAM and then write it out to disk. That's what the sound filer object does in pure data, and that's what this one does. Right now, Pd4P3 does not have a streaming write class, which I'm looking into doing, but that is sort of a different thing, because what this is doing is it writes all your data into the RAM, and then you copy that data in RAM to the disk. It's two separate processes, more or less. But when you're streaming it to disk, what it does is it writes a little bit into RAM, then writes it to disk, goes back, writes a little bit to RAM, writes to disk, and it keeps going back and forth until you tell it to stop, and then when it stops, it writes the file on the disk. And that is a very different thing, and that's usually something you do if you're recording an indeterminate amount of sound. And right now, Pd4P3 does not have that functionality, but other libraries do, if that's your core functionality. Otherwise, just write it into RAM and write it out. So this is not meant to mimic things like Pro Tools or Audacity, where that kind of functionality happens. Obviously, this is meant for real-time signal processing. So we want to keep everything in RAM to keep it as fast as possible. But if you did want to write to disk, this is how we're going to do it. We're going to copy some lines of code. What we need is this bit here. And I'm going to just copy it into my code here. And look at that, I was a bad coder. I forgot to free everything. So we have the world's largest memory leak here. And sound filer. And I forgot to free noise too. Oh boy. Sound filer.free. Wow. Okay, so I made a new sound filer object, called it wave, to basically represent the kind of file I'm going to write. I created a new integer, and I used this formula to create, which is the size of our file. And I used this formula, which is basically 4 seconds of audio times 2 channels. So it's stereo, even though it's mono, technically. If you wanted to, you could do 2 comb filters and have them going in stereo and do some really cool effects with stereo. But I'm not doing that. So I have to just double the channels by the seconds, which is interleaved audio, a stereo interleaved wave file, and the sample rate will be how many numbers basically it calculates. So you just need to get it. That is because we inherited PD algorithm, that means that this method is inherited and called get sample rate. Then we're going to make a new array to store our sound into, and that's where that's your sound file. That's the RAM. Okay, and then we just need a file name. So just make, this is going to be different depending on your system. Obviously don't use my system, so you're going to just basically put it where you want it. And Windows, you just have to do the double backslashes. On Mac, you don't have to do that. You use the /. So whatever, on Linux, you should already know what I'm talking about. And then we just need a sample counter to keep track of where we are in our recording. Okay, so now in the example, you see all we do is we basically say if the sample counter is less than the size, just write to our array. Otherwise, yeah, it just writes it straight out. And then we probably don't need that bit. And then this one says, but if the sample counter gets close to the size of the array, if it equals the size of the array, not it gets close. If it equals the size of the array, stop it and write it to disk. And then we just increment the sample counter. And that's what this little ++ thing does, is it basically increments it by 1. So it would be the same thing, I'll show you in a second, as just saying add 1 to itself. Okay, we don't need this. And we're just going to make a new double out. And in programming languages, you can't do this out equals 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 equals. You're just setting everything to the same thing. I like to do things this way. I think some people find it really confusing, but I think it's really clear that everything's just all set to itself. You know, you choose what you want. You could make a separate variable and then write it somewhere else. And then we need the stop write function / method, and that's from here, where we're going to make it private, and so that we can't actually call the stop write from processing. So we couldn't like make a mouse click stop write, unless that's something you really wanted to add functionality to, but then you could, it might create some problems, but whatever, it's experimentation. And this kind of gives you an example of what the write format needs. And just kind of basically it's the file name, the number of channels, the file type, and this is just how you have to do the file type, because I'm dealing with, I've actually borrowed the Synthesis Toolkit's file reading code and then incorporated it into my code, because it was already in C++ and it does basically the same thing as what Soundfiler does. It just reads in the bits and converts them. And then it needs to tell you the type of bit rate, bit depth, which is floating point, 32-bit. And then what to write it to, which is going to be the sound array here. Okay, so then basically it should start writing to the sound array, and we basically have this sample counter, which is going to just basically count all the samples until 4 seconds go by, which is going to be a lot of samples. And we increment our sample counter here. This is the equivalent to this, equals sample counter plus 1. It's the same thing. So it's just called an incrementer. And this means it increments it, and then the next time you access it, it is updated. All right, so if we get rid of that little bit, and now we have everything we need to record our input for as long as we want. If we want longer input, just make a bigger number here. And no. If we wanted longer input, just make a bigger number here. They're the same number, oddly. And that should write to our desktop. You'll see it pop up on the desktop as Pd4P3 test wave. Here we go. All right. And you heard that little glitch. That is inevitable. It might not do that every time, but it's trying to write to disk, and the processing might just be like, wow, you're trying to do way too much, and it just is going to glitch. Okay, so we got some, good output there, and then it tells us, hey, you wrote to the file, and this is coming from C++, which is why it's red. It's saying it's coming from a DLL, and that's what we loaded, right? Is our DLL. And that's how you do it. That's how you make, that's how you do two things, right? Is you make a comb filter and filter noise and record your output. I don't know if it overwrites it. I can't remember if it does or doesn't, but so just delete it if you didn't like it and do another take. And that's the solution. So if you came up with something really cool, send it to me. Otherwise, don't. I don't want anything unless it's cool. And if you have any questions, comment or send me a message. Or if you have issues like the code isn't working or something is giving you errors, put it in the GitHub. And I hope that this was helpful to you. Thanks for watching, and I'll see you next time.